Okay, let's begin. So we have been looking at the non-idealities we might have in our sampling switch. In the last couple of classes, we saw the non-ideality when the transistor is on. That is basically the on resistance of the switch. We saw that the on resistance for a normal transistor is a function of the input voltage. This is a good news or a bad news? Why? If this is function of the input, you saw that the output samples had non-linearity. So in the last class, we saw this gate bootstrap switch as one possible solution to reduce this effect. There the idea is to try to keep the gate to source voltage for the transistor constant by having a capacitor like this. And then we also saw that the on resistance also generates thermal noise. So which means finally when I have my track and hold like this, at the output along with the input I'll also sample some noise, some let's say Vn1 or something. What is the variance or mean squared value of this noise? Recollect it was kT by C, right? Again, I'll be using mean squared value and variance interchangeably, because if the mean is 0, mean squared value, which is the power, is same as the variance. Okay. And yeah, the power spectral density of this was actually white. And when was this valid? When did we argue that the power spectral density can be white? If the time constant is less than. See, remember when we argued that the power spectral density can be white only if we cannot make any prediction about my next input sample based on the current input sample, and that is possible when the samples are all uncorrelated, right? And that happens when the RC time constant is much smaller than the time for which the switch is on, which means that any residual output I have at the beginning of my nth clock cycle, effect of the previous sample decays instantly. So at the end of my clock edge, this impact will be 0, right? But this is always true. The noise power is kT by C. The power spectral density is flat only if you have within quotes a good sampling switch. Cool. So this is the major non-idealities with the on portion of the switch. Now it turns out even when the transistor is off, we can have some issues. So ideally, if the transistor is off, how do you want this to behave? How do you want this to behave when the switch is off? Open circuit. But it turns out in practice, when the transistor is off, you can have a small off capacitance. So which means even when the switch is supposed to be off, you have a case like this. Of course, this off capacitance will be very small, so in most cases this will not be an issue. But even if it is an issue, there are simple tricks. I will give it as an assignment for you to work out. Again, this thing is, or maybe I can ask you, right? So let us say, see, now let us say when the transistor is off, there is an off capacitance. So what will happen because of that? I mean, ideally, if this off, what can you say about the voltage across the capacitor? It remains constant. Now I also provide a path for the current input. So along with the sample, what will you see here? Let us say it is some Vn of n, the ideal thing you want. But now you also have a closed path like this. So what will happen? I mean, let us say this is a time varying signal. You have sampled it at this point. Okay. So the output ideally should have been held like this. But now what will happen? It will be changed from that point to some. Yeah. How will it change? Let us say this is what I call as Vn0. Let us say this is Vn0. Ideally, this is what you want. But now what will happen? Why will it decrease? No. Why? Correct. So, yeah, remember there is no discharging effect happening, right? This is again like, see, only if you have a resistive path to ground, you will have, capacitor losing charge, right? This is again putting, like another capacitor in series. So this is like he's pointing out, it is a capacitive divider. Yeah, it is not charge sharing. So the change here you see here, that will get coupled to the output. Okay. Huh? Correct. Yeah, it will be some, some V in whatever into V in of t times this capacitive division. Let us say this is. Ideally, it should be constant. Now, the changes you see here, that will get coupled by a small factor. So, let us say again, I'll just give you a hint. So, if this is an issue, this is V in of t. Okay. And remember, on chip, we always have differential signal. So, we also will have minus V in of t. Can you suggest some simple trick so that I can eliminate this term? How do you average? How will you add? Can you, yeah, I mean, that's all in words. Can you tell me how can I, this is the final thing I'm interested in. Here I'm having this, let's say V in of t times some alpha, right? Let's call this some alpha. Okay. Now I don't want to have this term at all. When I take this voltage, I should not see this. What can I do? I'm saying that I also have minus V in of t. No, I cannot add the two, right? This see, if I have, you are saying something like this, but this will be having minus V in 0, minus V in of t. If I add, everything will be 0. So what do you think I should do? I should add only this term. So how do you think I can add this term alone? Here, how will that help? Then during the sampling phase also we'll have some issues. I mean, see, why is this term coming second term? We have a capacitive divider like this, right? So if I, in principle, to make this term 0, what should I do? I mean, what should I add here to remove this? C of I cannot do anything. What I'm saying is, this is what I have. A plus B, I want only A. What should I do to that expression? I should add minus B. See, I'm saying I have A plus B. I want this to be A. I should add minus B. How can I add minus B here? Make sense? So you can go and add another off transistor here. This transistor will always be off. So only during the hold phase it will cancel it, and okay. So again you can work it out. I'll give it as an assignment anyways. So this is with the off state. Now it turns out not only when it is on or off, even when the transistor is going from on to off, you can have some issues, and that is a bit more serious than the off capacitance. So let's look at that. Let's say I have normal switch like this. This is the input. Let's say this is transistor M1C. To turn it on, what do I apply at the gate? It's an NMOS transistor. To turn it on, what can I apply at the gate? I'll apply VDD. Now when the switch is turned on, will there be a current in the transistor or not? When the switch is on, do you think there is a current in the transistor? There is a current. And in a MOS transistor, the current is proportional to what voltage? Mainly it depends on VGS, or not exactly, it is not just VGS, it is VGS minus VTH. Fine. Current depends on, let us say, VGS minus VTH. Right. Now again, without going into details of how MOS transistor works, which is not relevant to us, you can say that if the current is proportional to this, the MOSFET will also have some charge, and the charge should be proportional to what? If the current is proportional to VGS minus VTH, charge should be proportional to same thing, right? Rate of flow of charge is current. So let us say there is some channel charge here, I'll call it QCH, that is also proportional to VGS minus VTH ideally. But it turns out in practice, this is just an approximate relation. This will be a nonlinear function of VGS minus VTH. Okay. And here, as you see, the source voltage is approximately the input. So this is also a nonlinear function of the input. So the thing is, I mean, the mere fact that the channel charge is a nonlinear function of the input is not a problem, as long as this charge is not affecting me anyhow, right? But this is the state of the circuit when the MOSFET is on. Now let us say I turn it off. What will I feed at the gate? 0. Now when the MOSFET is off, is there any current flow? No. So what can you comment about the channel charge then? No current is there, the MOSFET is off, there is no charge. So when the transistor was on few moments ago, we commented that there was a charge. Now we switch it off, the charge disappeared. Where did it go? I mean, if the charge is there, there will be current. As simple as that. Two statements are correct. When it is on, there is a charge. When it is off, there is no charge. So where did the charge go now? Again, without going into a lot of things, we have some charge here. When I turn it off, it has to go somewhere. How many directions do you think it can go to? Either here or here, right? So, I mean, we don't know anything, we don't have to worry about it, but all I can say at this point is a fraction of this channel charge can get injected onto my sampling capacitor. Fine? You don't know how much, right? Why not? Why do you say, oh, I mean, why are you so partial towards this part? It can go either. I mean, I don't know. This could be close to 1. Alpha can be close to 1. I don't know. Frankly speaking, I don't care now. You just need to understand that some channel charge, it can be the entire thing or a small portion, something, will get injected onto my sampling capacitor. Okay? Correct. But we don't know what is the source resistance here and stuff. Right? So ideally, when I turn the switch off, if you don't consider the effect of this channel charge, what will be the charge stored in the capacitor? Ignore this extra channel charge. When the switch is working fine properly, the voltage stored across it should be C times V in. Okay. Now what we are saying is, along with this charge, I am also injecting a portion of the channel charge. Right? So the voltage across the capacitor is what? What is the voltage across the capacitor? If I know the charge, yeah, so V in this entire charge by C, so this is what I get. And as you see, this will now be a nonlinear function of the input. Right? So the problem is not that I am having some channel charge getting injected. The problem is because this charge is a nonlinear function of the input. Okay? So charge injection as such is okay, because if this channel charge was a constant, that is irrespective of the input, I inject the same charge here, then we are adding an offset, not a problem. Or even if this charge was directly proportional to input, you will result in a small gain error, which is also okay. The problematic thing is that this is non-linearly dependent on the input. Okay? So this is the problem we'll look at, which is signal dependent charge injection. Now of course if you go and use a gate bootstrap switch, right? So I put a capacitor here and do this, then what can you say about the gate to source voltage? It's VDD, it is some constant. So here I told that my channel charge was a function of VGS minus VTH, and in a normal MOS transistor the source voltage was input, you had issues, but with the gate bootstrap switch this term is okay, constant. But unfortunately story doesn't end there, because it turns out MOSFET also has one more terminal, which is the body, substrate or bulk, whatever you call it, right? And in most CMOS processes you don't have provision to connect the body terminal of NMOS to any arbitrary potential you want, because it is all shared by the same, this is all shared by all transistors. The body terminal is common to all NMOS transistors, so you connect it to the lowest possible potential, which is ground typically. For NMOS this is what you do. You don't have provision to connect it to anywhere you want, and because of this now you see you have a non-zero potential between source and this body terminal. Yeah, source, body, then body, right? But what happens if there is a non-zero VSB? Some of you might know already. Yeah, what happens? It turns out if this changes, the threshold voltage changes, and the threshold voltage is a non-linear function of VSB, so it follows that this is a non-linear function of the input. So we'll still have some non-linearity because of this channel charge. Okay. So let's
easily get away with this thing by connecting body with source.
In principle, yeah, but in most cases you can't do.
There are
because the way it's constructed is we have a common substrate on which all NMOS transistors are fabricated, most cases. Oops, cool. So let's see how we can go about solving it. So let's say I'll redraw the same thing. So this is Vin. So again, to remind you, the issue is because I'm having some charge getting injected, and also this charge is a non-linear function of the input. Okay. So my effect is I have non-linearity. Cause is twofold, right? So if I can address one of these causes, in principle I can avoid this problem. So, but it turns out this is something that you cannot do anything about, because that's how it is. It's a fact of life, you can't change anything. So let's see if we can do something about this thing. Right? So right now I know for a fact that I have some channel charge, and we have to live with the fact that this channel charge is non-linearly dependent on the input. But when I turn the switch off, if I can somehow make sure none of the charge goes here, I'm safe, right? So again, without going into a lot of details, I want to make sure no charge goes here. So when I turn the switch off, what can you say about the looking in impedance I should have? If looking in impedance is infinity, nothing goes. So I have something that is like this. How can I make this impedance infinity? Let's say I can't change this thing. I just have the two terminals. Basically, let me ask you this way. I have these two. Right now I connected it like this. Huh? Yeah. Oh, infinity is open circuit. If I do this, I don't provide any path for the charges. So if I don't provide any path for the charges, okay, so that's the solution. What you do is, before turning off, what should I do to the capacitor? I should open the capacitor. So when I turn it off, the circuit should look like this. There should be nothing here. If I do this here, the charges will come and take a diversion and go back. Okay. So that's not what will happen, but so now let's see how we can do that. So let me draw this again. I have input, Okay, I'll draw the capacitor horizontally like this. As of now we were doing this, fine, but now we just told that when I am turning this switch off, I should not be connecting it to ground. What should I do? I should open it. So I should not be connecting it to ground all the time. What should I put here? I should put some kind of switch. The switch connected to ground. What kind of switch I will use here? NMOS transistor. And let us say I'll call this M1, M2. So I call this clock 5. Now M2, do you think it should be switched before M1 or after M1? Before M1, so I'll control it with the clock 5E. We'll call it early version of the clock. So if I sketch the clocks, let's say this is my clock 5. Now ideally my early version of the clock should turn off before. So in principle, if I just make sure the falling edge drops before, I'm good. But oops, like this. But instead of generating a clock like this, it is much easier to advance both edges. So in practice we do this. Of course, now if you have 5E, I delay this and generate 5. Just pass it through a bunch of CMOS inverters and then get 5. So this is called bottom plate sampling. For obvious reasons, because the switch at the bottom plate of the capacitor is what is sampling it. And also, from these clock waveforms, can you tell me what time instant I am sampling the signal? I mean, with respect to these clocks, at what, when 5E goes off. Remember, when in this phase both the transistors are on, I am tracking the signal. It is when I am turning it off, it's like you say freeze to the capacitor, and then it kind of freezes the voltage, right? So let me just mark it here. So these guys are the actual sampling instance. So to summarize, first what we do, we have both M1 and M2 to be on. That's when we are tracking the signal. We turn off M2 and then we turn off M1. And when I do that, I see that any channel charge from M1 does not have a path to flow here. So there will be no channel charge that is getting injected. I'll say no Now at this point, I thought someone will ask a question. So again, since no one is asking, I'll ask it and answer. See, remember, what is the first switch I am turning off? M2. Now when the M2 is off, I mean when M2 is on, do you think it will have some channel charge? It will also have some channel charge. When I am turning it off, this path is still active. Huh? We can have anything, we don't know. That's what I'm saying. It is not as complicated, I mean, it's not as trivial. If it's open circuit, we know for a fact. There is no closed path. Right? So as of now, even some channel charge from M2 can go here. So do you think that is a problem? Why? Yeah, but please recollect, is charge injection a problem, or what kind of charge injection a problem? If the charge depends non-linearly on the input, is where we call this a problem. That's where we draw the line. So when M2 is on, what can you say about its gate to source voltage? Huh? It's VDD. Threshold voltage is also fine because source is grounded. So this guy, do you think it's dependent on the input? This is basically a constant charge. Okay. So of course when you turn it off, I'll have QCH2 injected, but that's okay. Because there is some constant charge that I am adding every time, that is like an offset. So now of course this ideally works well, but in practice there is one minor catch. Let's just look at that. Let me copy this. So let us say initially I have both switches to be on, and then I turn off M2. Okay, so I am looking at a case where M1 is on and I have turned off M2. Now ideally when M2 is off, it is supposed to be opened like this, but in the beginning of the lecture we saw there can be a small off capacitance. So which means now when you go and turn off M1, it is not a pure open circuit. So let's see what we can do, right? So first tell me, if when the switch here was on, what was the charge stored on this plate of the capacitor? C times V in. Okay. Now when I turn the switch off, of course some channel charge from here will get added, but we'll not worry about it because that is not nonlinear, right? Now we have some channel charge here. I turn off M1, some fraction of this charge will get added there. So let me call that fraction as some beta times QCH1. Okay. Now this beta times QCH1 goes like this, let us say. So what will be the additional charge I am adding to this plate? Beta QCH1, great. Now similarly, what can you say about the charge added on this plate? That's also beta times QCH1. Remember, two elements are in series, charges will be same. Current is rate of flow of charge. If current flowing through two elements in series are same holds good for charge. So now what is the problematic term here? This guy. So if I want to eliminate this, what kind of operation I can do on these two? If I subtract, I am fine. So I will either do QC minus QC off or the other thing. Right? So that begs a question, how can you add or subtract charges? So let me take you back to your class 10th or class 11. So let us say I have a capacitor C1 charged to some charge Q1, another capacitor C2 charged to Q2. How can I add the two charges now? I mean, remember, whenever it comes to charge, think of current, because current is basically rate of flow of charge. If I have two branches like this, wherein I have two currents flowing, how can I add the two currents? I'll join it and say that this is I1 plus I2. So similarly here, what can I do? I'll put it like this. If I connect these two, the charge stored on this node loosely is Q1 plus Q2. So they call it, show it in a different color. So we make this connection, then I'll erase it. The total charge is Q1 plus Q2. On top of it, if I go and ground these, what will be the voltage at the node X? The total charge at that node, which is Q1 plus Q2, by what is the total capacitance at that node? Fine. So now let us say I take same case. This is C1, Q1, C2, Q2. Now how can I subtract two charges now? Remember that if this plate here is charged with positive charges, this is having the exact negative thing. So what I'll do is basically go and flip the connection like this. Because right now this plate sorry, the charge on this plate will be minus Q2. Okay. So if I call this node as Y, this will be Q1 minus Q2. So again, if I go and ground these two, what will be Vy? It's okay. No. It is the same thing. The total charge is this. The total capacitance, I have both of them in parallel. So now let's get back to this. So here, what can I say about the charge stored on this plate? If this is plus QC, I mean, if the charge stored on this plate is plus QC, what can you say about the charge stored on this plate? Minus QC. I also know charge stored on this plate is plus QC off. So how do you think I can subtract charges? I mean, this plate is having minus QC, this plate is having QC off. I have to subtract QC and QC off. What can I do? I mean, or first of all, from this, can you tell me which operation is easy to do right now? This is easy to do. So if I go and just look at the total charge at this node, what is that? That is basically, yeah, QC off minus QC. Fine. Now in addition, as before, if I go and ground this node, I can now find the voltage Vx. What is Vx? Yeah, if I do the thing, what do you get? Yeah, Vx is basically Qx by C plus C off. And this you do, you get minus C by. Okay. This is fine. I mean, here the subtraction happens inherently because this node contains minus QC and plus QC. I just look at the total charge at that node. That inherently gives you the difference between the charges, and then you take the potential. I kind of ground it and look at the potential difference. Of course, for all practical purpose, this is approximately minus 2. C of will be much smaller. Okay. So now if I, okay, let me just rewrite this. So what we are essentially doing is this. I have the sampling network like this. I will show with ideal switches for now, or maybe I will show with MOS transistor. It's okay. This was my original sampling network. So instead of having one sampling switch, I decided to do bottom plate sampling so that no channel charge from this gets injected here. So if I call it M1, M2, if I clock it at 5, I clock this at 5E. But then I find that when this guy is off, I have a small off capacitance. So which means I still have a closed path for this channel charge to go that can impact me. So I decide to look at the total charge at this node, and to measure the voltage, I go and ground it and find the voltage, right?
But addition of ground won't lead to the discharge of.
Yeah, that's what. I cannot always connect it to ground, right? What do?
You will connect the switch.
I'll have to put a switch here. It is connected to ground. I'll use what kind of switch? Okay. So now that begs a question. What should be the clock phase for this guy? 5x. Huh? I mean, let me draw the clocks. Let's say this is 5. 5E. 5E is early version. So in terms of these two, can you tell me how should this look like? Delayed version of 5. So you are saying, let us say something like this. Okay, if that happens, yeah, if this happens, you see what happens, right? You have a clock phase where all three of them are on, right? If you generate 5x like what was suggested, you will have a case where all three of them are on, so you will have complete mess up.
5x should be on just at the falling edge of.
Okay, so you think about it, I'll just tell the deal, right? See, sorry?
5 bar.
5 bar. Okay, so let's say you do 5 bar. How do you get 5 from 5 bar? Inverter. Inverter will have some delay. So which means again you will have a case like this. You will have a case where both 5 bar and 5 will be on. Right? A small instant for which this will happen. This node will be pulled both by this switch and this switch. That is something you cannot avoid because generating a complemented version of the clock will have a small delay. Do the same thing, right? Same thing, right? So 5 bar will be even disastrous. So if you do 5 bar, let's say you get something like this. So once again you have the same thing. So the bottom line, the point to note here is when phi or phi E is on, my circuit is doing something which is basically sampling and tracking the input. Sampling is happening during this phase. Now during phi x, I am trying to ground it and measure the sampled voltage. These are basically two different operations, right? My circuit is operating in two modes. One is where I am trying to sample. In the other phase is where I am trying to measure what is my sample voltage or process the sample voltage. So these are two different modes of operations. I should not be doing both of them at the same time. Okay. So we should have a case where the clocks are non-overlapping. That is, both phi x and phi cannot be active at the same time. So you cannot have a case where both these clocks are high at the same time. So which means only after, let us say, phi becomes low, I will make phi x high. This will guarantee that there is no overlap. Fine. So the clocks will basically look like this. I'll draw with ideal switches now. So I'll have, or I'll draw it here. It's okay. So let us say this is my one clock. My phi x should basically look like this. So when phi goes high is when phi x, when phi goes low is when phi x goes high. Similarly, when the second clock goes low, the other clock goes high. No, not when M1 was on, right? Why do you want it to be on? No, this after M1 is off. I mean, we are looking at the issue of charge injection that happens when the switch is turning off, right? So I'll redraw the circuit now. So I'll draw with ideal switches. So now we are sampling it like this. Let me call this as clock phi 1 and phi 2. I'll say this is phi 1. This is phi 1 early. This is the bottom plate sampling that we started with. This was to make sure when this switch was turning off, the nonlinear channel charge here doesn't get injected. But then we found out that because of the off capacitance here, you might still have some nonlinear channel charge getting added. So we decided to add another switch here and ground it and look at this voltage Vx, which was approximately minus. Is that fine? So now the question is, how do you generate these two clocks? Because input to your circuit will be one master clock, you have to generate all the other things, and that is actually not a major deal. Let's maybe briefly look at it. So let us say this is your input clock. something like this, and you want to generate phi 1 and phi 2 that look like this. So phi 2 should go high, only this goes low, something like this. So basically only after falling edge of one clock I have this rising edge, falling edge of this triggers rising edge of here. Fine. So let us say my input clock is phi, I have to generate phi 1 and phi 2. Okay. Now let's look at phi 2. Phi 2 is going high only after phi 1 is going low. So other way to see is when phi is 0 and when phi 1 goes to 0 is when I should have an active high for phi 2. So I am having a case where when two signals are 0, I have 1. What kind of a logical operation does this? NAND or NOR? When both of them are 0, I should get 1. NOR gate. Okay. So what I'll do is I'll generate phi 2 as a NOR version of phi and phi 1. Okay. So maybe I'll replace this, say it's phi 2, phi 1. So I'll take phi, I'll also take phi 1 and then do this.
Phi is for the M2.
No, this is the main clock. Okay, this is your input clock. You have to generate the other clocks from this. Okay. Because in practice you cannot tell your customer that you feed in two clocks like this, they should never overlap, blah blah blah. No one will do that. Whatever is required from your end, you should generate it. The input will be just one clock, say approximately 50% duty cycle. You have to generate everything based on it. So this is the master clock, and you generate it.
Just taking the master clock phi and then phi for the main switch I use phi.
No. Everything is now like this, right? Now the sampling is happening in one phase, phi 1.
No, sir, I'm just talking about phi E.
Correct.
Will be the master clock.
No, phi is an early version of phi 1, right? So basically what you do is you can call this as early and then take this, delay this and call it as phi 1. Okay. So similarly you can do for other phi 1 also. Look at phi 1. Phi 1 is going high when phi is high and when phi 2 goes low. Correct? Only when this goes low and this is high, it is happening. And the clock phi being active can be thought of as phi bar being low. So let us say you generate phi bar, some delay is there. Okay. So if I can view the situation as this, when phi bar is low and when phi 2 is low is when I make phi 1 high. Okay. So here I have to get phi 1 when both of them are 0. What do? I do NOR of phi bar. Yeah, it is an SR latch, but it is not operated as a latch here. So of course to generate phi bar from phi, you put a inverter and that kind of something. Is that okay? Now of course here the delay for which or the time for which these two are not overlapping depends on the delay of this NOR gate, because as we saw, after this goes slow is when phi 1 goes low, phi 2 goes high. So it is the delay in this NOR gate that is giving this delay. Okay. So this is, let us say, a T NOR gate. Now if you want to increase this delay, you go and increase delay in this logic. You make the NOR gate more and more delayed, or you can add, CMOS inverters in this intentionally. So you can take this. You can intentionally add delays by putting inverters like this. Then you boost it. And you can call this early version of phi 2, early version of phi 1, and you generate the other two clocks like this. So again, to summarize it, the sampling network right now we have is like this. The circuit operates in two phases. In clock phase 1 is when we are trying to sample, and for that we are doing bottom plate sampling. So if this is clocked at phi 1, this will be clocked at early version of phi 1. And to process the sample data, I ground this. You want this? If you want to increase the delay of this NOR gate, can design the NOR gate to have more delay, or we can just do this. That's what. So in one phase we are doing this sampling. In the other phase is where we ground this and look at the total voltage at the node X, and this was approximately minus V. So now you have this. Now we can go and do any processing on the sample data. So let me do this. So let me draw. In phi 1 we have a case like this.
To put it in words, the phi X must be on and phi 1 is off, right?
Both of them are off.
The M1, phi 1 and phi 1.
Phi and phi are off. That's what we are doing. That's why we are doing this non-overlap clocks.
But weren't we considered about that QCH ready to ground?
Which one?
From M1.
Yeah. The point is, it's again nothing changed, right? So if I show here, so I am plotting that here, right? So let us say in one phase, this is the circuit we have, right? Now, end of the clock phase phi 1, we turn off this switch. No worries. And then you turn off this switch. And that because of the off capacitance here, you will again have some charge injected. So you do the second clock phase phi 2, wherein you take this voltage. Nothing changed. It is the same thing. The two clock phases I am now calling as phi 1 and phi 2. Earlier I was calling as phi and phi x. I have relabeled them as phi 1, phi 2. And the bottom line is, these two clock phases cannot overlap. Both these clocks cannot be active at the same time. So we have to generate the clocks so that they are behaving properly. Okay?
So the charge training isn't due to like phi 1 being turned off. It can happen any time.
No. It will happen only when phi 1 is turned off.
But so therefore, that's what I'm saying.
What?
At phi 2 you will have charge training from M1, right?
No, why? Then see, the circuit operates like this. First, we have this. Second, we open this. So we'll have a small off capacitance. Then let's say this is V in, and then we open this. The small off capacitance you have here. When you turn it off, is when, yeah, of course, some channel charge can get injected. Yeah, but the solution for that is what we saw, right? We subtract the charges. We are looking at the charge at this node, right? So, and for that only we are looking at the charge at this node. So to process the voltage, we ground this and look at this voltage. Okay? Is this clear? Fine?
So phi 2 goes on when phi 1 is off.
Yeah.
And phi 2 should go off before like phi 1 gets off.
Correct. That's how we are generating the
Phi 2
clocks.
gets off, there would be a, like Vx is like when phi 2 is on,
Mm-hmm.
Vx is equals to minus V.
Correct.
When phi 2 goes off, there could be some channel.
Yeah, channel charge. But again, when phi 2 is off, yeah, you are right, channel charge gets injected. But is that a problem? It's not dependent on the input. We are only interested, we are only bothered if the channel charge is dependent on the input. These switches are actually no-brainers. You don't have to worry about it. Okay. So now let's quickly finish it. So this is the, okay, let me take it. Yeah. So this is how we are operating in both clock phases. First clock phase we are sampling, and now we know charge injection is all taken care of. Let's not worry about it. And we look at the total voltage here. And if you look at the total voltage here, no issues is there, right? So now if you want to feed this to a second stage, and let us say my second stage is here, and if my second stage is drawing any current, what will happen to the charge stored in the capacitor? I mean, the capacitor is storing some charge. If you start to draw any current, you lose the charge. So you cannot directly connect it to my second stage. What should I do? You should put a buffer here so that the current here is 0. You preserve this voltage, buffer it, and feed it. So this is something you can do, but it turns out when you implement a buffer in open loop like this, you will have a lot of non-linearities. So we will not do this. So the practical thing what we do is what I will explain now. So let me take this alone. Correct. Yeah, of course you have to design so that the input capacitance is small. Right? What is used as buffer? Common source, common drain, common gate. Huh? No, common source is an amplifier, right? Common, you think about it. Okay. Yeah, you can use it something, but the point is, if you use a buffer like that, turns out without going to details, it is more non-linear. We don't do it in practice. So.